right?
Yeah, go ahead, Prakash. I think, yeah.
Okay, yeah, okay. I think this screen should be visible right now. Welcome back, everyone. So what I'll do is now go over the second worksheet, which is on radiometer characteristics. So just a short recap, what we did in the morning session was calculate the current in an antenna feed, and we found out how one can extract power. Now what we'll do is we'll relate the intensity of radiation that is falling on an antenna and see what kind of electrical power is received by the radiometer. So the antenna feed is what takes in the noise or the noise from the radiation outside and passes it on to the radiometer, which with which we can measure it. So going by this definition from this book on essential radio astronomy, which by the way is a good reference. You can it's the most of the content is available online for anybody to access. Um, you could find a lot of things that were covered today uh, described over there as well. A radiometer is essentially a receiver that is used to measure average power of the noise from a radio telescope in a well-defined frequency range. Now, let's try to visualize what's happening. Let's say there is a sky distribution of intensity. So that is what is represented over here. This is a picture that I found in the NRAO website, where what they have done is put a background of, instead of the visible light intensity distribution of the sky, they've taken a radio image, a large field of view radio image, and then made it look like that is what we are seeing in the sky. So you can imagine such a distribution that an antenna would see, and you can describe it in terms of the intensity as a function of the two position angles in the sky. Now, what one can do is introduce an antenna, a simple dipole would do for our purposes. And what we want to know is how does this antenna actually view the sky, and what is the power received by the antenna as due to the intensity that is falling on it due to the combined intensity. So what one needs to understand is the intensity will couple to the antenna's electrical power through something called the effective area of the telescope. Now, I'll do a give a small illustrative example of how to understand what this effective area is. So what we'll do is we'll take a dipole antenna. First, we will see it as an emitter, a transmitting antenna, and we'll see what the power pattern looks like, and then try to understand how it would be for a receiving antenna. So So the steps are essentially we'll try to see what are the motion of charges in the feed element of a dipole and how that leads to a distribution of electric field around it and hence the power. Then we'll see how we can translate that to the motion of charges in a receiving antenna and we'll see uh, the distribution of the effective area. So So again, to the right, you'll see a small schematic of a dipole antenna. But now the difference is it's a transmitting antenna where an oscillating voltage is actually driving the charges inside the elements and causing the currents that produce radiation and it's being emitted out, right? That is how it works, except the acceleration is given by us right now. So you can see that as the charges move from basic electrodynamics, we know that along the direction of the acceleration vector, you won't see any radiation. And the maximum electric field strength of the transverse electric field strength, which causes wave propagation, is maximum in a plane that is perpendicular to this axis of the dipole. And if, for instance, theta is the angle that we are defining with respect to the axis, then the transverse electric field is proportional to sine theta. and the power pattern obtained by essentially squaring the electric field is sine square theta, and the distribution is how you see in the bottom figure. It's a polar plot where it essentially plots sine square theta. And if you see in 3 dimensions, it would form like a symmetric torus. And it essentially shows that along uh, in the at the middle of the dipole, along the horizontal axis, the power emission will be maximum, and it will go to zero at the along the axis, following a distribution that goes as sine square theta. Now, once we understand this, it's easier to relate it to a receiving antenna, where what's happening is we have electric fields that are falling on the antenna element, a dipole element, and you can see that when the electric field is parallel to the axis, it will cause the charges to move and have the maximum effect. Whereas when the electric field is perpendicular to the axis, it will have almost no effect to a contribution towards the current for a thin wire like dipole. And for a general angle theta, it will be proportional to sine theta. That is the, the electric field um, reduced by a factor of sine theta will be the one that will drive the current. So you can see the equivalence over here. Uh, the so the effective electric field will follow a sine theta dependence for the incident electric field, and hence the effective area, which we are defining as how well it can receive radiation along different directions, will follow now a sine square theta form, which is will be exactly like the power power pattern of a similar antenna if it were transmitting. It is a proportionality, but not an equality, the effective area and the power pattern. So what we have is this effective area, which is actually designed according to the application we are interested in. We could have something this broad that is looking at all the directions, or most of the directions pretty broadly distributed. Or we can have ways to concentrate the effective area such that um, we are only focusing on some area of the sky, or a solid angle above the telescope, rather than looking all around. Now, once so this effective area is dependent on the shape of the feed element, as well as uh, and once that is set, we could always change or redistribute this effective area by having reflecting surfaces like a horn or a reflecting dish and so on. So a dipole antenna which has a distribution of sine square theta for the effective area, proportional to sine square theta for the effective area, as shown in the picture above, it could be placed at um, with the appropriate reflecting surfaces or inside a horn, such that the effective area redistributes uh, such that it has a much narrower distribution, as you can see in the bottom figure, which is essentially if you design the horn of the antenna right enough, it will look something like this. So there is this, once the feed is designed, one can, I think effective area is conserved, and you can use reflectors to redirect it such that you can get higher effective area than it was without the reflector. Now, just by these relations on the effective area should be somewhat obvious, that if you integrate the effective area of the over the entire 4 pi steradians, it could be expressed as average effective area times 4 pi, or we can also define maximum effective area, and let's say we divide that by the average times 4 pi, you'll get something called the beam solid angle. That's another quantity that you can that characterizes a telescope essentially, where it sort of gives an idea of how well the effective area is localized. Okay, so now we are back to our setup where we have an intensity distribution in the sky. The intensity couples to the antennas through the antenna's effective area, and hence it generates a power in the antenna, which is an integration over for a general case. It will be an integration over the effective area and the intensity distribution of the sky. Now, the factor of half in front is because we are looking only at one polarization with a single dipole. So this is the most general formula. What one can go ahead and do is define in the Rayleigh-Jeans limit, you can take the intensity of any particular source or any particular region of the sky, see how much flux it gives, and try to assign a brightness temperature to it. This is something you must have heard in the previous lectures too. But essentially, you're equating the intensity you're getting in a small band, and you're equating to, or you're finding out which temperature black body would produce a similar amount of flux as the intensity that you see. And hence, in the Rayleigh-Jeans limit, this would be the expression. It will be 2 kBT by lambda square. And what that allows you to do is convert that intensity distribution of the sky into a temperature distribution. And you can have a expression like this for the power that would be available at the antenna. Now, this allows us to, in principle, define an antenna temperature. That is something, again, you would have heard it in many of the talks and you will be hearing. This module, actually, when you go through some of the sections, it will make more sense as to why we are yeah, why we are defining antenna temperature at all. But for now, let's assume that we have a power received in a particular spectral range, and we can always convert it to a temperature by dividing it by the Boltzmann constant. And we can call that, instead of using power, we are just using equivalent term. Since it's a constant proportionality, we are referring to it as temperature, and that we are calling as antenna temperature. And from previous expression, you can see that you can hence get a relation between the antenna temperature and the brightness temperature of the source that you're looking at. This is the most general case. Of course, right now, it may not mean too much as to why we are doing this, but once you figure out using the worksheet, how one can calculate the total effective area, for instance, or in special cases where the beam is too narrow and pointing towards a broad source, or a source is completely um, covering the range of the effective area of a telescope, then we can simplify it and we can get a much more clearer relation between the antenna temperature and the brightness temperature of the source we are looking. So yeah, I won't say much more on this here because I mean it's better when you work it out. But what we have here so is we have defined the antenna temperature, and then we can say the power measured power in the antenna. Okay. What I'm saying is what you can do is if you have this antenna and a radiometer, you can measure the power that is there in the antenna. You can always equivalently call it in terms of the antenna temperature. You will have access to the effective area of the telescope, either because of its reflectors and all that. It could be this well constrained or well localized, or it would be a broader distribution. But in principle, you'll have this value. And using this equation, in principle at least, you can model the intensity and try to get uh, the intensity that is producing the power in your antenna. This is just, I'm summarizing the general setup. What one can do is look at the special case of a black body and try to see how much power is generated from observing a black body. For this, there is a good little thought experiment one can do where you start out with the lossless antenna, which is, it doesn't have any internal resistance, but of course it will always have radiation resistance because if charges are going to accelerate, it is going to radiate. And that is a form of resistance. So other than that, it does not have any other resistance. And it's surrounded by a black body, and the entire effective area is looking at a black body of temperature, uniform temperature T. Now, in another cavity, there is a match resistor. When I say match resistor, the resistance is chosen such that the resistor's resistance matches the radiation resistance of the antenna that we have in the uh, other path. And now they are both connected by a transmission line, which allows only electrical power transfer across it. So under equilibrium, uh, we'll have a condition where there will be no net transfer of power, so that the energy distribution will be the same, power distribution will be the same in a resistor of matched resistance and the antenna of a particular radiation resistance. Now I'll have to, okay, I'll leave it at this. Again, this is something um, you can use the setup and try to find out how the temperature of the path corresponds to the temperature of the antenna that we observe. Now that is again an activity, you will do it and you'll understand. But as long as you understand the setup, this will again be explained in the worksheets. And I just wanted to get you familiar with it. Um, Now, what we have in this setup is essentially a relation between the power distribution in an antenna and the power distribution in a resistor. And we have shown that it will be equal, at least in this particular setup. At this point, it would be good to know what is exactly the power distribution in a warm resistor. If it's maintained at a particular temperature, what would be its power distribution? For that, there's another experiment where you take identical resistors. The experiment is similar to the previous one where you have them at the same temperature. And here they're connected through by a transmission line of length much greater than the wavelength of interest to us. So we are measuring essentially the power distribution in a particular uh, frequency band. Again, at equilibrium, there will be no net power transfer. And what we'll have in the transmission line is essentially standing waves. And standing waves are these are created when opposite moving waves of equal amplitude and equal frequency combine, and you can create these standing waves. It's just a tool that allows us to actually enumerate the number of energy distribution in different modes that exist inside a transmission line. That's why we are uh, going about this particular experiment. So we focus on the transmission line. We know there's no power transfer, so the only energy distribution is in the standing waves in the transmission line. And we have chosen the length so that we are in a regime where there's no, um, the quantization effect is not too much. We essentially have a continuum of states. Yet still, because we have a particular length of the transmission line, we are able to still count the states at lower wavelengths, apply the same formula for throughout um, its frequency range, and essentially get the power distribution in a frequency band. So it essentially, as you'll see in the experiment, it will essentially help us count these energy states. So what we'll do is we'll count the number of modes that exist in a frequency band. It will be more obvious at when we start counting from uh, the lowest wavelength it allows, or rather, sorry, the largest wavelength it allows, and count up. For instance, the modes that are allowed are shown by the schematic at the top of this circuit. There, the nodes will have to go to zero at the ends of the transmission line for it to be a standing wave there. And one can essentially count the number of modes exist in a particular frequency range. Once we have Once you have that, you can calculate the average energy per mode using the Boltzmann law. And you can calculate the time it takes for, you know, this energy to transfer through the transmission line. And essentially you get the power right out of it by multiplying the number of modes per frequency band by the average energy to get the average energy per frequency band. And you convert that to power by trying to see how long it takes for it to traverse a particular distance. So in summary, what you would have learned, what will become clearer at the end of working with this worksheet is that um, you'll see how electromagnetic spectral intensity is converted to electrical power in a frequency band. And we'll see how a natural way of talking about electrical power in a radiometer is to use refer to something called the antenna temperature. And then we'll also see the equivalence between antenna noise and the noise of a warm resistor. Together, it will sort of form a consistent set of ideas that give an idea of how what kind of electrical power is generated in the radiometer uh, due to the radiation that is being sensed by the antenna. So you'll notice that the order of these sections are sort of reversed in the worksheets themselves. I mean, Desh was the one who convinced me that this is the right order to go, which I agree. I do think this is the right order. Uh, because there is a small problem that in the worksheet it might give you the false impression that the black body is somewhat special and some of the relations you're finding out applies only if you're looking at a black body, but it's more general than that. So between this presentation and that worksheet, I hope you get a more consistent picture. You should always refer back to these presentation when you're working on this the worksheet. Okay, so I'll briefly go over what to do with the voltage data that is provided to you with the OT radio telescope. But before that, maybe we can take some questions on this.
So are these slides made available to us? Because I'm not sure.
Yeah, sure, I can make it available. We'll put it in the same folder where,
Okay, that would be great. Thank you.
yeah. And you guys all know that these videos are going to be on YouTube, right?
Right, thank you.
So you can listen to that too. We'll do some bit of editing, for instance, cut and paste here and there today, since it was jumbled up a bit. But either way, it should be available.
So one more query, like while solving the worksheets, especially that one which was antenna field electromagnetism, can we start working from the scratch and do the necessary derivations and then do the worksheet, or do we have to submit it just as a template you have provided after filling up the blanks
No,
which
no,
you
I want you to do what you think is best. If you would add things to it, that would be great. Actually,
yes,
we
sir.
could
Then
even
I
extend
yeah.
the worksheet. We could even extend the worksheet for future uses and make it publicly available. And if you could contribute towards that,
Great,
that
sir.
I'll be
Great.
more than happy.
Okay, fine.
Yeah.
Uh, I have two questions related to your last slide where you used two resistors. Uh, uh, the last thing.
Yeah. I'm trying to go back and play and go. Yeah.
No, before that, I meant the yeah. So
This.
I there are two things that I couldn't understand. One is what is the significance of having L much greater than lambda? I mean, I couldn't uh, understand that one thing. And second thing, will this not be only able to measure low energy modes the way if we arrange it with L much greater than lambda? I mean, how are we actually then going to measure uh, high higher energy modes? I mean, so it's basically related to the fact I'm not able to understand L much greater than lambda here.
Actually, I would say it's the other way around. We are setting it so that we are able to achieve pretty much continuum distribution across all modes or all frequencies are allowed. So what it does is This, when we are counting these modes at very low lambdas, no, not very low lambda, these high lambdas or low energies, what we are doing is establishing a way to count these numbers. We are essentially using this to determine what is the functional form of number of modes per frequency band. But we are not actually we are not interested in this distribution at such low energies. Eventually, we are interested in the distribution of number of modes per unit frequency at higher energies. It's just that this gives an easy way to count them and then use only the expression in the higher energy limits. Does that make it clear? Because here what happens is the quantization makes it so that most of the energy just goes into these very specific bands. But in a resistor, it would be at all frequencies, essentially. Does that make sense? Like in a resistor, it won't be quantized like this. We're using this quantization in this transmission line so that we are able to count it. We can determine the functional form of delta n by delta nu, apply it in the regime where the effect of quantization is negligibly small. Essentially, there are a lot more modes per frequency band. It's a simple tool for that. Desh, maybe you can make things.
Yeah, I just want to continue on what you said. Just say it again, that for convenience of computation, one wants things to be quantized so that one can count. But in doing that, the graininess is to be reduced to very fine level so that there is a effective continuum. Okay, and that is done by setting L much larger than whatever frequency of interest, so that the graininess in frequency is very tiny. So you practically have a continuum, but you have the advantage of estimation using the discreteness.
Yeah, I got it. Thank you.
So L going to infinity is what one is looking at, okay? Where it's mashed to R, okay? So there are, in equilibrium, there are no reflections. Everything is absorbed.
Right.
Okay, maybe I can go to the next one. If you, of course, this you'll have to work on the worksheets before you get more doubts, but you can reach us anytime with if you are facing any problems. So for the, okay, I'll have to switch the window. Okay, do you all see my browser now? There should be a Python notebook visible.
Yes, sir, we can see.
Yeah, okay, good.
We can see.
Sure. Okay, so for this, so what we have done is, I mean, it's mostly dishes. We have voltage data available from ORT. I mean, I was conflicted whether to say what object we are observing, but I think at this point we have advertised it quite a few times, and it's better to know what object you're using, you're looking at, so that when you do see the signal, you can be sure you're on the right track. So we are looking at essentially a pulsar data. What we have here are, I mean, I've made the Python notebook such that it essentially describes what are the steps you need to do take to do the basic analysis. I've given the algorithms, and also in the case of Python, if Python is your preferred programming language, it will be great because I've also given what sort of commands you can use and given links to it. Can I get an idea of how many people are not familiar with Python? You guys could raise your hands. Familiar in the sense you may not be able to work with it. Could be one, or do you use any other language like C, C++, MATLAB, or there are
So it's
different
fine with C. C
tools?
is better.
Okay, so you do your plotting with GNU plot or what?
Sir, for plotting, actually, I prefer Origin.
I see. Okay.
Okay.
I haven't had experience with Origin. Does it allow data plotting? I'm assuming it does. Okay, never mind.
Yes, sir, it does. Like
Most of them should do.
it
Yeah,
does.
yeah,
It
yeah.
does.
Okay. And the rest of you too, I assume that you have some programming language that you do use. You're not completely new to programming. I'm pretty certain that's true. So I would suggest, I mean, you are free to use whichever programming language you're comfortable with, but you will notice that Python is not very hard to use either. If you know a programming language, you just have to know the algorithms. You search for equivalent syntax online, how to do a particular thing in Python, and you can always do Python with relative ease. And here the algorithm is given, and in many cases, the links to the commands that would be useful in Python to get that done is also given. So you could either give it a try over here in a collab notebook or use your preferred language. It's fine. Either way is fine with us. But of course, you'll have to access this file. You can open it in Colab or as a Jupyter notebook locally on your system, and you can at least go over the algorithm generally. Okay, so what we have is about 5 data files. I think all 5 of them. I haven't looked personally into all of them. I think 2 of them, 1 or 2 of them I've looked into. It's essentially voltage data from ORT. Um, so just a brief description about the data file itself. It's a time series that is given in 2 columns, one for the UT radio telescope north and one for south. Um, and these are raw voltages. The units themselves are arbitrary, it's not calibrated. The frequency range of observation was 326 plus or minus 8.25. And if I'm not wrong, Desh, this has been down converted to 0 to 16 megahertz, right?
Yes.
Okay, yeah.
Or effectively, even though it was at another frequency and it is
Right.
during the sampling, that conversion has automatically taken place. So we can assume
Right.
for.
Okay, yeah. So eventually you can express it when you plot it, and you can show them between around 326.5 megahertz. But when you do find the frequency, constituent frequencies while doing Fourier transform or something, it will be from 0 to 16.5. So the data is sampled at Nyquist rate. It has 2 real voltage measurements for the lowest period of interest, or maximum variability, between the maximum variability time scale. And that you can calculate by using this formula. The length of the data is about 1 second, may not be exactly equal in all the cases. That you can again just see the length of the data multiplied by the time resolution that you get over here and get it. So initially you can look at some of the statistical properties that you've been hearing about. The voltages themselves will be Gaussian distributed. Sorry, I noticed so you can visualize the time series, you can plot the voltage data, next what you can do is you can draw a histogram of these values and uh, check for yourself that it follows a Gaussian distribution, or if it does deviate, you can still report that, and we can try to figure out what could be causing these deviations. And if you take the mod square, or just the square of it, you'll get the power values. You can see what distribution that follows as well. So I have linked actually, okay. If you're gonna be using, before going into the details of those, I'll just talk about some of the things you need to take care of while setting it up. If you're going to run it on Collab Notebook, which you can easily do, you don't really have to connect it to your local runtime. You can run it entirely on Google servers. It works just fine. I've tested it. And then you don't have to worry about plotting these on your system yourself, although these are fairly straightforward and simple libraries. What you can do is this data is all saved in Google Drive. And in principle, you can directly access these files from the drive location and download it and analyze it. So that is what this piece of code does over here. You don't have to worry too much about each step here, but I have tried to comment it as much as possible. But if you follow these steps, choose a particular file ID, then at this point of the cell, the data will be all loaded. All you have to do is put it in a data frame and give the titles that you prefer, and the data is loaded at this point here. Now with the voltage time series, you can do plots of histograms, time series, the same thing you can do with power. I was thinking whether to show you sample plots or not, but I mean, there's pros and cons to both. The thing is, it's nice to work on some data not knowing how it's going to look and plot it by yourself and be at least mildly excited when you see some signal or see something that you expect it to do and so on. If I show a lot of plots, I feel one would be too focused on trying to match something that has been shown and worry too much about uh, whether they've got it wrong or right or wrong. What I could suggest is that you start playing out with the data. And if you want some confirmation, you can contact any of us and we'll be able to help you out to confirm, or if there is a problem, we can point it out, or we can confirm whether you're on the right track. Okay, you'll see that a lot of these are hyperlinked to resources that will be useful. For instance, when you convert the probability, the distribution of voltages to a distribution of power, what sort of form does it follow? It's close to exponential, but I mean, it's close to an exponential. So you can plot the power time series, power histogram, and then you finally would come to the a main way of looking at data, that is the dynamic spectrum. Now, even before that, I should tell you how to get the spectrum. Yeah, so, okay, no, that comes under dynamic spectrum. So what you can do is, so you have these voltage data that is varying in time, and you'll have to select appropriate number of these voltage samples and Fourier transform to get the spectrum in that particular time bin. So, so that's what this sort of thing describes, how to choose the right number of frequency bins and decide and then find out what is the time bin that you end up with, how many points you should take to do the FFT for a particular number of frequency bins that you want to have. And it also gives you which commands you can use to get all these, like essentially the FFT or getting the frequencies of the FFT. So essentially it uses a NumPy, if most of you who use Python would be familiar with it. The only things, so till this point, pretty much till this point, plotting the dynamic spectrum. So once you regroup the data, you have this voltage time series, you regroup it so that you have chunks of voltage samples that you're going to take Fourier transform and convert to spectrum in that bin. So now you'll have a series of spectra in time instead of just voltages. Of course, the time bin will be larger now, according to the number of points of you took for FFT. What you can do is you can plot this as something called a dynamic spectrum, which is how the spectrum varies with time. Now, this will be something that will immediately start showing you if there is something interesting in your data. I do explain here that if This is essentially high resolution data, so it might be useful at various points to appropriately bin them so that your signal to noise also improves and your signal is more easily visible rather than you having this unwieldy large set of spectra that you're having a hard time even to plot and to see the signal in it. So till this point, it's mostly plotting to the point that you get the dynamic spectrum. And once you get the dynamic spectrum for pulsars, you'll see some clear clear patterns. What will happen is probably, I don't know whether it has been covered yet, uh, about dispersion of the signal that is coming from source. I think Desh covered it, although I'm not sure. So what happens is the lower frequency signals, even if uh, emission happens at all frequencies at the same time at the source, because because of dispersion due to the interstellar medium electrons, the lower frequency signals will be delayed compared to the high frequency signals. And this follows a form of 1 over nu square, the delays. That is also sort of all explained here. So what that means is when you look at the dynamic spectrum, you'll see that if you see a signal, the signal will be delayed as you go to lower frequencies. And another thing about pulsars that you'll notice that the signal will have a periodicity. So we have chosen a source over here, which has a few periods within the 1 second of data that we have. So you should be able to see these two patterns very clearly, the dispersion of the signal and also the periodicity. Now, the only thing, now you will go to the source characterization where essentially you'll do two things: correct for this uh, dispersion delays, and then you'll fold it by the period of the pulsar and get integrated pulse profile. Now you can do the first step. Once you have the dynamic spectrum, you'll get an idea of what the maximum delay is for the frequency range you're observing, with which you can sort of get a rough estimate of the dispersion measure, and you can actually correct for it, um, assuming a rough value. Similarly, you can look at the plot and find a rough value of the period. You can use that value. You can get an integrated profile just to make sure you know the algorithm is working right. But then what we would like you to do is get a more accurate value, for which you would essentially uh, take a matrix of values, two-dimensional distribution of DM and dispersion measure and period. And what you'll do is uh, try to repeat this procedure of getting the integrated profile and try to see where the power distribution is the narrowest, so that the profile is the narrowest, and hence the intensity square and added will be maximum for that profile. So I should say that so far I've explained till only finding the approximate DM value and correcting for it. What I'll do is I'll add a little bit of section about how to improve on these values, and then it will be a lot more clearer. For now, you can still get started. I'll update you as soon as I add that little section about how to optimize and get the best fit values using essentially this method of um, looking in a matrix of values around the rough value of DM and period. Okay. So I think, yeah, this one, it's better to start getting your hands dirty, start working. You can do a little bit each day, and then what I'll do is I'll today set up a folder where you can put your updates as it comes along, so that I can also check if you have a question. I can refer to it and then help you out if you're getting stuck somewhere or if you just want to make sure something is right.
So can I ask some questions?
Go ahead. Yeah.
Okay, probably the answers are in these sheets. I have not gone through them. My first question is, what is the time delay between the northern and the southern array? Meaning, how is it compared to the time resolution of the data?
Is zero.
The delay is 0.
Yeah.
Or
The relative delay has been adjusted for the source direction, okay, to catch the same wavefront. So there is no further adjustment required between the north and south signal.
so we generally we do that adjustment, or meaning in this data that adjustment has already been done.
Well, in the telescope setup itself, the signals traveling from some direction which is at an angle with respect to the vertical, the instrument vertical, will be seen, the arrival times will be different, correct?
Oh yes, that
for the two halves. That has been already corrected for in preparation of, comparing these two outputs, okay, so that they are on the same footing, they correspond to the same wavefront.
Okay, so we need not worry about.
Yeah, you need not worry about the left uncompensated delay. Okay, normally in reality you need to compensate for it, but it's already compensated. And for convenience, we have recorded these two separately. We could have now more often than not, people actually combine this already and record only one output. But this also gives an advantage of you seeing how the interferometry would work, right?
Otherwise, the statistics will be different for the northern and southern. Meaning, if we do the determine the statistical parameters.
Statistical parameters will be same, even with a small shift. The ensemble is not going to see much change.
Okay. So if I determine the variance or the mean of,
there could be some differences in the gains, okay, of the amplifiers in one chain from the other, which might show up in the magnitudes being little different.
Little meaning how, meaning what is the range of that difference? Meaning, is it considerable?
It should not be considerable. Okay, ideally they should be comparable if everything was adjusted correctly.
Okay,
but you can even comment on that.
So from this, my next question is, if I want to improve the signal to noise ratio of the signal,
right?
So can I add the power from the two halves?
You might even add voltages from the two halves. Okay, which might even give a better coherent picture. You might gain factor of 2 in sensitivity because you will be using twice the collecting area effectively. Instead of doing a power addition, which will gain you only √2.
So voltage will give me,
because the voltage is also coherent.
Because I was thinking that if I'm adding the power, it will give me an incoherent addition.
Correct.
As I saw in your previous talk.
Right.
So
here you can treat the bigger aperture as a whole, okay, by adding the voltage signal or the fields received by the two halves, as long as they are brought in phase, which they have been done already.
Okay.
By adding them, you would actually have an effect of increasing the collecting area by a factor of 2.
So that is
combination, and that gains you straight away that factor in sensitivity.
Okay. And another one is, can we determine the period derivative P dot from this much long data segment?
Yeah, this is only 11 pulses, okay, in 1 second. And typical derivatives, okay, period derivatives are of the order of part in a 10 to the 15.
14, 15 years.
Okay, so to see appreciable difference, even at the level of a sample, which is typically about fraction of a microsecond, right? Or few tenths of nanoseconds. So to see such a shift in the data, you can do the calculation. You will require at least 10 to the 6 seconds worth of data.
Okay, minimum this much long.
Before you can begin to notice the difference. Okay.
Okay.
That is even in the ideal case. Okay, there is in the absence of noise and so on.
Okay. And
So,
one,
so that's typically a day. Okay.
that's 10 to the power 6 is, yes. So that much long data. Or with gaps also, I can do that.
Yeah, with gaps, there is no worry as long as you have information extending to that span.
That much span, yes. Okay, and here the bandwidths are like 8.25, meaning the
Plus or
first,
minus.
yeah,
So
plus minus.
16.5 megahertz. Yeah.
How is this chosen? Meaning, is there some calculation? Because
No, this is
8.25
chosen for convenience. This was ideally chosen because the fastest rate at which one could record the data dictated the maximum bandwidth we could use.
But meaning generally for convenience, we take whole numbers. And then when we are down converting it, we are doing it at double the range.
Yeah,
Okay,
so the whole number here is the 30 number to remember is 33 megahertz is the sampling clock.
Okay.
Which
So
is
16.5
able to sample half of that number as a bandwidth without aliasing.
So plus minus is 16.5. Okay.
No, it's 0 to 16.5 sampled due to Nyquist criteria at 33 megahertz.
That will give me this number. Okay, sir. Done. Thank you, sir.
Sir, I had one doubt.
There are people with some previous experience with this data as well. So it is best if you work with your group members and maybe some of them can help each other out.
Sir, actually, hello.
Yeah.
Sir, I had like a doubt here. Like, how will we measure 3 sigma value of UT? And also, like, whenever we receive, like, analyze the data, how can we verify whether it is over 3 sigma value or not? Because unless it's over 3 sigma value, we can't like directly comment over whether it's complete, like whether it's signal, actual signal or a noise. So
I mean,
how
you can
can we
check
work
it
on it?
yourself. It's way more than 3 sigma, but essentially you'll see some signal, the profile, let's say. Even without folding, you can try to ascertain what is the noise level away from the pulse and at the pulse, and you can calculate a SNR and you can report that, how high it is and whether you believe it or not.
You can estimate the noise level when the pulse is not there, okay? Or even for the entire data, and use that as a guideline to assess what is significant and what is not.
Okay.
So if you see excursions well above that threshold, okay, then you can treat them as not random fluctuation of the noise.
Okay.
Yeah, that's a good way to put it. So you'll see that there's a lot of spurious signals too that will go way above 3 sigma, but that's not really any real source. It's probably RF, radio frequency interference. So any other questions you have, or we can end this particular session? Okay, anyway, this is something you have to work on yourself a bit, and you definitely will have more questions. You can reach out to us, talk among yourselves within a group, that forum that we created as well. Okay, I'll stop sharing, and maybe you guys can take 5 minutes off, and then we can get started with the next one. Next session on Fourier transforms by Desh. Sounds good?
Yeah, so we meet after 5 minutes, right?
Yeah, that's fine with you, right, Desh?
Yeah. No, in fact, I think let them have a short break so that
Yeah.
for both the reasons, as a break as well as changing the topics. I think there was somebody, Akshay had raised his hand. I don't know whether it was part of, in response to your question about the Python or.
Yeah, I think it was raised for some while. Akshay, do you do you want to ask something, or you can lower your hand?